how's everyone feeling?
You have to still get to me. He's on my side. I'd Russell need an open. And then he'd be on my side coaching because I'm PC.
All right. Any questions before we get started today? All right. Last time we were working our way through the last pieces of chapter 7. We talked about work done by friction, efficiency. Last concept we addressed was power. We looked at the formula for it, and looked at a conceptual example. I'd like to give you guys an example of how to use the formula first before we switch gears and start talking about something else today. So just to kind of reiterate from last time, power is the measurement of the rate at which work is performed. You can also think of it as the rate at which energy is used. The main formula for power is work over time. Again, you are doing work using energy over time. We measure power in watts. 1 watt is 1 joule of work done every 1 second. So a 20-watt light bulb does 20 joules of work every 1 second, or can also be thought of as it uses up 20 joules of electricity every second. So that's what the wattage means on any of your appliances. And every process has some sort of a power rating that will tell you the rate at which it is accomplishing its goal. The higher the power output, the quicker it's usually able to do its task, but the more energy it's going to take to do so. And then the less power, the usually slower it will take. Questions conceptually? All right. So, quick example. I'll put this one to you guys to work on your own or amongst yourselves for a minute before we talk about it. We've got 2 people who are going to lift boxes upstairs. We looked at a few cases of the work done when lifting a box. Both people are going to be hauling these boxes up 30 meters vertically. So the displacement, the delta y, is going to be 30 meters. And the 2 people are carrying 2 different boxes. Person number 1 is carrying a 1,000 Newton box. And that is its weight. That is its weight pre-calculated. And they are going to run up these stairs in 1 minute. Person 2 is only carrying a 500 Newton box, so their box weighs half as much. And their time to run up the stairs is half a minute or 30 seconds. Bless you. I would like you guys to calculate for me real quick the work done by each person, and then separately the power output of each person. And we'll compare the 2 together. Again, work either on your own or amongst yourselves for a second, and we'll see what answers you come up with.
it's times 3. Oh, this one.
All right. How y'all feeling? So which of these two people does more work in this scenario? Person one, that is correct. You quickly discuss that answer. The work formula is still force times displacement. Let's call it delta y since they are lifting objects straight up. So we have to take since they're moving up, we have to take that vertical displacement and multiply it by the vertical force they have to exert on these boxes. That will be equal to the box's weights, which are already pre-calculated here. So work 1 would be the weight of box 1 times the 30-meter change in height. So that'll be 30,000 joules of work done by person number 1. Work 2, person 2 is only exerting half as much force for the same distance, so person 2 will do half as much work. So, second question, which of these two is more powerful? They're the same. Does everyone agree? All right. To demonstrate how they are the same, power formula is again work over time. So for each of their respective power outputs, we need to take their work and multiply it by the time it took that specific person. So I just got the formula here twice, once for person 1, once for person 2. For person 1, they do 30,000 joules of work in 1 minute. I'm going to make that 60 seconds rather than 1 minute, because we like seconds. And that is 500 watts. 500 watts, which is about 2/3 of a horsepower, give or take. Person 2 does half as much work, but in half the time. They do it in half a minute, which would be 30 seconds. And that does turn out to be the same power output. So even though person 1 lifts a heavier box, does more work, the fact that person 2 did their task faster causes them to have the same power output. When it comes to the metric of power, speed is arguably as important as raw force output. So, when you're looking at, say, the power output or the power requirements of machines, think of that rating as not only, how effective it is at its task, but also how quickly it can do that job. But you should also think of it as how quickly it will drain its own energy. Because not only are they accomplishing 500 joules worth of work every second, they are burning up 500 joules of their own energy every second. And if one of them did have a higher power output than that, they'd get the work accomplished more quickly, but they'd also probably tire themselves out faster. So note that whenever you're looking for appliances, higher wattage appliances might be more powerful, but they'll drive up your electric bill. Does that make sense? All right. How's the concept of power feel before we switch gears for something else? All right. So that is, again, what I would call the end of Chapter 7. Chapter 7 would be, in my opinion, all about energy-related stuff, energy itself, work done, efficiency, and how power. We're going to switch gears now, moving on to chapter 8. And up till now, most chapters have been kind of a direct continuation of the last one. This one is kind of switching gears, thinking in a different direction. Chapter 8 is going to be about rotation and rotational motion. My original plan was to cover all of chapter 7 before the test. Just didn't end up happening quite that way. So the reason we were covering this week is because of that kind of arbitrary cutoff. I wanted test 1 to happen when it did so that assessment day and spring break didn't get in the way of you guys getting it done and getting to your grades. But now we're going to kind of change what we've been thinking about, change the way in which we are thinking about things. I would say we are now entering the second half of the course. So any questions or objections before we begin the discussion? All right. Now, up until this point, all the concepts we've been discussing have been linear in nature. I believe I've said that word a couple times in reference to motion. I want to make sure to redefine it really quick if I haven't done that recently. The word linear means of or referring to straight lines. The word is literally linear. All the motion so far has been in straight lines, either forward or backward in one axis at a time. But that's not the only form of motion that exists in this universe. Humans do often think of things as moving back and forth in straight lines, perhaps even moving in multiple directions at once. But that's not the only way that things can move. For example, behold the disembodied bike tire of science. In your professional, my bad, there was a magnet stuck to this thing and I forgot about it, and then it just flung off. In your professional opinion, as someone who has lived in this universe your whole lives, would you describe this wheel currently as moving? All right. Now, what is its current x velocity? 0. It's not currently displacing through space in the x-axis. What about y-axis velocity? Yeah, it's not displacing vertically either. So we agree that it's moving, but the terms we've been using to describe motion so far are kind of failing to describe this motion. Does that sound right? It is moving, but it is not moving one-dimensionally through space in any single direction. That's because this is rotating. And rotation exists. Rotation is a part of our lives. Every vehicle you will ever enter involves some amount of rotation. The planet you live on is rotating in several ways all at the same time. So rotational motion is important, and we have to use a different set of variables, a different set of logic to kind of describe it. It's not all new logic. I want to kind of paint a picture of how the ways we've been describing motion can still apply to rotation, but it does require a slight change in perspective. So, up at the front here, I just want to kind of say, everything up till now has been linear, and we are about to enter rotational. Sound all right so far? All right. Now, one more vocab word, actually. Linear refers to straight lines. Rotational refers to spinning or rotating. I'm going to be saying the word angular a lot in conjunction with the word rotational. Angular means of or referring to angles, which means this is just a synonym for rotational. The word rotational and the word angular are synonyms. And because I was taught both of them as synonyms, sometimes I use them interchangeably. So I want to get that out of the way right now. This chapter is about rotation. You can also describe rotational motion as an angular motion. And I want to make sure that you know that means the same thing. So when I say angular, I mean rotational, and when I say rotational, that applies to everything else that has the word angular on it. For example, your formula sheet has several things on it listed under the angular column. Angular also means of or referring to rotation. It's referring to the act of going through an angle change rather than a delta x linear change. So linear, of or referring to lines, angular, of or referring to angles. So I just want to make that vocab term clear at the front here. Now, when we've been discussing linear motion, again, all the stuff we've been doing up before now, you would think of linear displacement in terms of how far forwards or backwards you move in a straight line. We measure it with a meter stick, you measure it in units like meters and feet. If I pick up this bike wheel and make it spin in place, we again agree that it's not currently displacing in a straight line in any axis. We agree that it's moving, we agree that it is displacing somehow, but meters and x, y, z, etc. that's not describing this. If I asked you to tell me, how would you measure the rotational displacement of this wheel? How you would measure the amount that it is moving rotationally, how would you think to do that? How would you describe the magnitude, the amount of rotational motion that this wheel would undergo?
In degrees.
Degrees. The amount of degrees that it spins through. Does that make sense? We, in math, use degrees to tell us how big an angle is, how much spin something has undergone from a certain baseline. Angles are the measurement of angular displacement, rotational displacement. Again, angular and rotational are synonyms, so you can use either word there at the title of this slide. For linear motion, we would describe that as, the variable we used to use for that is delta x, and that again describes meters forwards or backwards in a straight line. If something is spinning, we instead describe its angular displacement, not how far it's moving forwards or backwards, but how much it has spun, how much it has rotated through. And since that's not the same variable, that's not measuring the same thing as delta x. Because again, we can agree, if it's spinning in place, it's definitely rotating some number of times, rotating through some number of degrees, even if its delta x is constantly 0. So for that reason, since the delta x is 0, but it is still rotating, we have a different variable for angular displacement rather than linear displacement. The variable for angular displacement is delta theta. That is the Greek letter theta. And depending on how much math you've had before, you might have used that letter in a math context, most notably in a geometry class. Does that look familiar? This is the same use of that letter. An angle measurement is a measurement of rotation. It's how much this line has rotated from this original position. And so when you measure angles, degrees, you're measuring the magnitude of rotation, the magnitude of angular displacement. So this delta theta is the same as if you've been using it in math class or geometry class. It's the same thing. So that's why we use the same letter for it. And even though it's measuring angles or amount of rotation rather than meters, we still kind of use and think about it in the same way, which is why it's located on your formula sheet here. All the formulas that have delta theta in them are located directly across from a formula that has delta x in it instead. As we go through this chapter, I'm going to keep comparing linear and angular to each other. We may be measuring angles and rotations instead of meters, but all the rules for how displacement and velocity work are still going to be intact. That's going to be what we're talking about this week. So just kind of going through this new variable, this new way of thinking. When something is rotating, instead of delta x meters forwards or backwards, you measure delta theta, the amount that it has rotated. If I take this wheel, this is why I had that magnet stuck to it. There we go. I've lost my magnet, unfortunate. Okay, I'm gonna make this bike wheel rotate, and I want you to measure with me its angular displacement. So this is gonna be its starting position, and to kind of help indicate where that is, I'm just going to put my right hand on the wheel, and it's not going to come off of this spot of the tire. So this is our starting position with my hand up here. And then I'm going to rotate it from here, up at the top, 12 o'clock, to, I guess I'm following a clock, so my left hand actually. Starting up here at 12, what is the magnitude of this displacement? 90 degrees, very good. 90 degrees or 1/4 of a rotation. There's a couple different ways you could say that measurement. And then how about from here to here? 360 degrees, also known as 1 full rotation. That is again the magnitude of angular displacement, the measurement of how much something has spun. This is how you measure displacement for a rotating object. You're looking at how much it spins as opposed to how far forwards it moves. You all right so far? Okay. Now, since delta theta is technically a new variable, it's a new thing to measure, I want to mention the units that it is measured in, and kind of like how for normal displacement, you could measure it in meters or feet, just depending on what tool you're using or who you're talking to. There's a couple different units for angular displacement as well. The main three that you will see include, I'm going to kind of go backwards here, rotations. You can just describe how many times something has fully spun. You could also talk about how many degrees it has rotated through. Again, from a second ago, 90-degree turn is 1/4 of a rotation. 360-degree turn is 1 full rotation. But there's one other unit that will come up, and that is the unit of radians. Does that sound familiar? Okay. Again, that's something you would have encountered in probably a geometry class. Radians is just a different unit for the same thing. Again, it's the relationship between degrees and radians is like the relationship between feet and meters. And since these are all three different ways of describing angular motion, like all three different units for it, I'm going to make sure that the conversion is on the board for you. You can convert any one of these into the other two. 1 full rotation is equal to 360 degrees, and both of those are equal to a number of radians equal to 2 times pi, the number pi. This is just the conversion from rotations to radians and from degrees to radians. It's a weird unit, I fully admit. But it's one we kind of have to use because a few of our formulas require its use, unfortunately. So 1 full rotation is 360 degrees or 2 pi radians. 1/2 rotation is 180 degrees or pi radians. 1/4 rotation is 90 degrees or pi over 2 radians. So radians is the unit and the 2 pi is the number. You can use the pi button on your calculator for that. But if your calculator doesn't have a pi button, you can just use 3.14. We will practice that conversion whenever it comes up. There's a few formulas that will require its use. But that is how we measure angular displacement. That is how you measure the amount that something is spun. Sound all right so far? All right. Now, kind of like how there's multiple ways to describe linear motion, like there's multiple facets to it. There's displacement for how far you move and velocity for how fast you're moving. The same is true for rotational motion as well. So there's another rotational variable I want to go ahead and discuss, and that is that of angular speed. Angular velocity is also a fine way to describe it. Because if I pick up this wheel and make it spin again, you could not only tell me, how many times it rotates before it stops, you could also tell me the speed at which it is rotating, right? You could tell me how many times it spins per minute, or something like that. And in fact, if you drive cars, you've at least subconsciously been measuring the amount of times your car's tires spin, because most cars have an RPM meter, rotations per minute. That is a measurement of angular speed, the speed at which something is rotating. Linear speed, or linear velocity, either or in this case, is displacement over time. It's how quickly, how far you move per second. Angular velocity and speed work the same way, except instead of how many meters forward do you move in a second, angular speed is measured in how much do you rotate per second. And again, your car's RPM meter is measuring this. It's measuring rotations per minute. Bless you. So RPM is a measurement of angular speed, rotations per minute. So this is the formula for angular speed, and it is literally just the velocity formula, but like the mirror universe twin of it. See the similarity, I hope? It's literally still displacement over time. It's just angular displacement instead of linear displacement. So again, it's how much you've spun per second instead of meters traveled per second. And since angular speed is also technically a different variable than linear speed and linear velocity, it has its own symbol too. That being this. Does anyone know what letter that is? It certainly looks like a W. It's technically lowercase omega. Uppercase omega is the horseshoe, lowercase omega is apparently the world's worst Snidely Whiplash mustache. I would not fault you for just calling it W though. I've had plenty of people call it W over the years. I tend to say omega just because there's other W's in this class on your formula sheet. So I say omega to try to avoid mixing those up. So if I read this out loud, I'd say omega equals theta over t, or omega equals delta theta over delta t. We got a lot of Greek in this class. But you can call it W and I won't cut you off for that. So again, this is the variable for angular speed. And you would measure this in units like radians per second or rotations per second. Those both are measuring the same thing here. Rotations per minute is a fair one too. So again, these are all just ways of describing angular motion. How far you've moved angularly, how quickly you're moving angularly. So these are just the metrics we use to describe it, kind of like how we went through how we described the linear motion at the start of the class. Sound okay so far? All right. Now, we've got this conversion up here. This will remain. And again, on tests and stuff, this would be either on the board or in the problem or on your formula sheet.
We'll put the formula for angular velocity up here as well. Angular speed.
Bless you. Since these are new concepts and formulas, let's get in a little bit of math practice on how these apply to the real world. We are going to take a wheel and we are going to watch it spin 180 times in 1 minute. Take a wheel, get it spinning at 180 rotations in 1 minute. So, first question, I promise I'm not trying to trick you with this one. What is the angular displacement of this wheel after 1 minute? That sounds right. Hold on. I hadn't done it in degrees. Times 64,800. Yes. 64,800 degrees is absolutely one way of describing the total rotation of this item. Call that delta theta. So, that is how many degrees something will rotate through if it goes through 180 full rotations. Now, how's that number calculated? What other ways can you describe the magnitude of this rotation?
360 radians?
Not quite. 360 is the amount of degrees in a single rotation. Now, to kind of show where that number came from, if you haven't calculated it for yourself yet. That number was derived by converting 180 rotations into the corresponding number of degrees. So I'm just kind of using that as a conversion factor here. I want to cancel out rotations, replace them with degrees. 180 times 360 degrees gives you 64,800 degrees. So this is the same number of degrees as this many rotations. And that is one way of describing the total amount of angular motion that takes place here. There's two other units that I can think of that you can use to describe this motion in. What might they be? Well, actually, you said one of them. You said radians. That's another unit that you can use. And to show how you would find that many radians, I'll do that conversion as well. Because turning rotations into radians is just a conversion. 180 rotations. One rotation is equal to 2 pi radians. I would set it up like this to cancel out rotations, leave behind the unit of radians. So to do this correctly in your calculator, you do 180 times 2 times pi. Pi is a number here, it's not a unit. Now if you left pi in, that would be, oh, I think I see what you were doing there. My mistake, I wasn't visualizing it right. If you left pi in, it would be 360 pi radians. Which would be correct, as long as you leave the pi there. Now, keeping in mind pi is a number. If you fully solved it out, that would be 1,130, just round it up to 1, radians. Radians get shortened to rad. Just want to make that clear. So, these are both correct. Sorry again for misunderstanding your answer. Those are both correct ways of saying it, but note, if you're doing this conversion, pi is a part of it. So you either leave the pi there or you multiply the pi in. Make sense? All right. There is one other way to describe this motion, one other way that you can write down an answer for delta theta. And the 180 rotations is itself already a measurement for delta theta. That is the amount that it spun, just in units of rotations. So there are 3 different units that you can use for angular displacement. Sometimes I might ask for a specific one. If I don't ask for a specific one, typically I'm okay with any unit that you come to first. Just make sure that whatever unit you choose to give your answer in, your number is correct for that unit. Again, the pi for radians can be tricky. So, 3 different units for angular displacement. The 180 itself does describe it as long as you keep that in units of rotations. So, any questions or issues with the angular displacement of the wheel, how much the wheel has spun in this example? All right. Next question, what is the wheel's angular velocity, given the information here?
6 pi radians.
6 pi radians per second, very good. Omega equals delta theta over delta t. So really you just got to pick one of these delta theta answers and divide it by the amount of time. As discussed, 360 over pi is a correct way of writing this delta theta. And since it's spinning for 1 minute, that would be 60 seconds. So 360 times pi radians over 60 seconds would give us 6 pi radians per second. As one way of describing this motion. And again, you could multiply the pi in. 6 times pi is 18.8. So if you multiply the pi in, you get 18.8 radians per second. So that is correct for that particular unit. But if I'm not asking for a specific one, you could take any one of these and plug it in here. You could do 64,800 divided by 60 and tell me degrees per second. You could just leave the rotations in here and tell me rotations per second. That should be 3 rotations per second, I think. And again, the unit that your car uses is rotations per minute, in which case 60 seconds is 1 minute, and that would just be 180 rotations per minute. So this is one reason why units are important. It's important to know what units you are given and which ones your answer would end up in. Because I would accept multiple different correct answers for this as long as your unit is right. So think about the unit you are using to describe the motion. And actually, we kind of already did the last part. If one rotation is 2 pi radians, we've already found the radians per second. Actually, you guys worked ahead of me. I was expecting to calculate it in rotations per minute first. So, how's this sound? All right. Now, it is absolutely okay if thinking rotationally is kind of weird. I found that humans tend to perceive motion in straight lines whenever possible. When you think about something moving, you do tend to think moving forwards or backwards. We're three-dimensional beings. We're not really rotational beings. So if this takes a second for your brain to kind of grasp it, that is totally okay. Again, we're moving into the second half of the course. Things are starting to get a little bit weird. What we're going to be spending the next week or so on is describing rotational motion and also looking at how it is similar to and also different from linear motion. We're not going to cover every single angular thing on your formula sheet. We only have so much time in the course. There's a lot of things on my standard formula sheet labeled as angular that we're just not going to do within this class, because I use the same formula sheet for most of my classes. So we're not going to cover all of these. I just wanted, as the last thing today, show you that there's a bunch of different ways to describe angular motion, and even though it's about degrees and radians and rotations instead of meters, all of the old logic that you used to use for linear motion is still true. On the left here is all the linear formulas we've used for motion so far. We've got normal linear displacement and that first 4 list of formulas on your formula sheet: velocity, acceleration, and then displacement while accelerating. All those same concepts exist within this angular world. You've still got displacement, velocity, acceleration, displacing while accelerating. Same concepts, same logic, just for spinning instead of straight lines. And we're not going to cover all of them. Really, for this week, we're just going to focus on these 2 and then look at some places where these are applied. I just want to illustrate that rotation's not that different to the motion we've been describing. All the logic, all the terms we've used so far still are true, just for rotations spun rather than meters forward. So I'm trying to illustrate this as a comfort, as a point of comparison. We're not throwing everything out, we're expanding. Does that make sense? All right. Today's Wednesday. On Friday, we'll continue looking at the similarities, move forward into a couple new rotation topics. Let me know if you have any questions leading up to then, and please have one today.